Introduction to Solutions in Aqueous Reactions. Ion concentrations with an insoluble product. The purpose of this video is to go over the mixing of solutions composed of different soluble solute compounds that result in the formation of an insoluble product. So we're going to look at how to get started in the process, finding the concentrations of the soluble ions, determining the insoluble ion, determining the concentration of the ion in excess, and finally working through an example. The place to start in this process is to determine the ions present in the solution from the chemical formulas of each reactant species. So you need to go back to some of your pre-chemistry stuff and look at the formulas and say to yourself what ions are composing these reactants. Since the reaction is a double replacement reaction, you want to write the chemical formulas of each of the product species, and we'll go over a little review of how to do that. Then you want to balance the chemical equation by mass, apply the solubility rules to determine the solubility of each product species, and finally identify the presence of the solid precipitate. Now, I'm going to run through all the calculations here, and I know it's basically going to be reading these at you, but I want you to get a general idea of what we're going to do before you actually see this in action. So think of this part as the processing part. So the first thing that you're going to do is determine the moles of reactant cation and anion that react to form the soluble products. So we're just looking at the ions that are going to be ions as products. The way that you're going to do this is that you're going to calculate the total number of moles of soluble ions by multiplying the molarity and the volume associated with the soluble ion together. Now you've already done this, so this should not be something new. You're just finding the moles of the soluble ions. Then, once you have the moles of the soluble ions, you're going to divide the moles by the total liters of solution to find the concentration, otherwise known as the molarity, of the soluble ions. And we just did this in the previous video. Then this is where things become a little different. Calculation 2. Consider the moles of the reactant cation and anion that react to form the solid precipitate product. So now we're going to try to figure out what two ions are coming together to make the solid. Once the moles of both the reactant cation and ion forming the precipitate are determined, identify which ion is the limiting reactant and which ion is the excess reactant. Now, once you figure out what the limiting reactant is, it's pretty simple, because the limiting reactant ion will be completely consumed in the formation of the precipitate. Thus, the overall molarity of this ion will be 0 molar. No other calculations are needed. Once you find the limiting reactant, that's done. The molarity associated with that ion will automatically be 0 because it's going to be completely used up. There will be no ions in solution by itself. It is all part of the solid formed. Calculation 3. The amount in moles of the excess reactant ion remaining in solution can be determined by comparing the initial amount present before mixing the two reactant solutions to the amount used in the consumption of the limiting reactant ion during the formation of the precipitate. Now, I'm not going to lie. This sounds a little confusing here. It's okay. I'll show you how to do this specifically. Then, once you have this difference in moles before it reacted and moles after it reacted of this ion in excess, we're going to find the concentration, the molarity, of the excess reactant ion by dividing the moles of ion remaining in solution by the total volume of solution. So calculation 3 and calculation 4 can be a little difficult until you see it in action, and I'm going to start doing that right now. Okay, so here's our example problem. Determine the concentration, so again, we're looking for molarity, of each ion present in the solution formed by mixing 80 milliliters of 2.25 molar BeNO32 and 40 milliliters of 1.25 molar KOH. Now, where to start in the process? Well, the first thing that you're going to need to do is say to yourself, okay, I have a reactant, and that reactant is BeNO32. NO3 2. Fantastic. That's one of my reactants. And my other reactant is KOH. Awesome. Now, this is going to be a double replacement reaction. So when I think of these two formulas and I break them up into their ions, well, I'm going to have Be plus 2, and I'm going to have NO3 minus 1, and I'm going to have K plus 1 and OH minus 1. So now what I'm looking at here in a double replacement reaction is that the Be and the OH are going to come together to form a product, and the K and the NO3 are going to come together to form a product. So if I write these new formulas over on the product side, and it doesn't matter which order you put them in, I'm going to write KNO3 first, plus, and then I'm going to take the Be plus 2 and the OH minus 1, and I'm going to cross them down, and I'm going to get BeOH subscripted 2. Okay, great. So now I have a chemical reaction. I know it is written correctly, so now I need to balance it. So I'm going to start out by looking for parentheses, because that's what I always do. Well, we're over here, so over here I know I have 2 hydroxide ions, and over on my reactant side I only have 1, so I'm going to put a 2 in front of there. So I have 2 hydroxide ions on both sides. Now I have 2K here, so now I'm going to put a 2 in front of here, so that gives me 2Ks on both sides. And now that trickles over to the NO3, so now I have 2 NO3s, and oh look, I already have 2 NO3s over here. And then finally I'm going to check my Be's, 1 Be here, 1 Be here, and it's a balanced reaction. Fantastic. The last thing I need to do is think about solubility. So in the beginning, they tell you that these first 2 reactants are definitely soluble in water. If I wanted to put in states, I could. So aqueous, KOH is a strong base, definitely aqueous. But then when we think about the products here and we think about the solubility of the products, KNO3, we know that's super soluble. Group 1 metals are going to be soluble. Nitrates are always going to be soluble. So we're going to put an AQ here. But the BeOH2, that's definitely insoluble. So we're going to put a little S here. So this is going to tell us a lot of information. These are the 2 ions right here that are going to make up our insoluble product. So we're going to consider those later. And then the K plus 1 and the NO3 minus 1 are going to be involved in our next calculations. So let's consider those next. So our first calculation is going to be determine the concentration, again, the molarity, of each ion present in the solution formed by mixing, and here's our 2 reactants, and the molarity and volume for each one. We're going to start out by considering the moles of reactant cation and anion that react to form soluble products. We're going to calculate moles first, and then we're going to determine the concentrations of each. So let's start out with K plus 1. So K plus 1, let's figure that concentration out. So if we look back at the information given to us about potassium, we have a molarity of 1.25 and a volume associated with this of 40 milliliters. So we know that molarity is equal to moles over liters. So if I take that molarity, which is 1.25 molar, and I multiply that by its volume, which is 40 milliliters, which I'm going to change into liters, that will be 0.04 liters. And I know that the ratio of potassium to hydroxide is 1 to 1. So I know that there's 1 mole of ions associated with this. And then I'm going to divide it all by the total volume. So the total volume in here is 80 milliliters plus 40 milliliters, which gives me 120 milliliters. And when I convert that into liters, it's 0.12 liters. So the concentration associated with K plus 1, if I multiply together 1.25 times 0.04 times 1 and the total thing divided by 0.12 liters, that concentration will be 0.417 molar. And really, I'm done with the concentration of potassium now. I've figured it out. It's totally soluble. This is the concentration of potassium ions in my final solution. Let's now go look at the nitrate ions. So concentration of NO3 minus 1. I'm going to do the exact same process. So now I'm looking at the nitrogen ions. My molarity is 2.25 molar. The volume associated with this is 80 milliliters. So this is going to be 0.08 liters. And now the important thing here is that I have to multiply this whole top by 2 because the ratio of Be to NO3 ions in this compound is 1 to 2. Then I'm going to multiply the whole thing by 2, and then I'm going to divide it by the total volume of 0.12 liters. So when I multiply all those top numbers together and I divide it by 0.12 liters, my concentration of the nitrate ions in solution will be 3.00 molar. And now I'm done with my soluble ions. Final answers right there, nothing more that I need to do. And frankly, we've already done this in a previous video, so this should not be new. This is a little new because in this case, we're going to consider the moles of the reactant cation and anion that react to form the solid or insoluble precipitate product. So that's the first thing we're going to do. We know the two ions that are coming together to form our insoluble product. We need to find the moles of both of them. Once we do that, we're going to identify which ion is the limiting reactant and which ion is the excess reactant. So let's start out with the two ions that we know are involved in the insoluble precipitate. So the first one is Be. So I'm going to put, because I sort of want these next to each other, so Be plus 2. And going back to writing our formula, molarity is equal to moles over liters, and we want to find moles. So the molarity associated with Be is 2.25 molar. Okay, we are solving for X. We're solving for our number of moles. The volume associated with this is 80 milliliters. So I'm going to convert that into liters, 0.08 liters. And if I cross multiply here, I am going to get 0.18 moles of Be plus 2. Fantastic. Moles of Be plus 2. Now, I need to do the exact same thing for the hydroxide because that is the other ion involved in my insoluble product. So I'm going to take the molarity associated with the hydroxide, which is 1.25 molar. Again, I'm going to solve for moles, just like what I did with my other one. And I'm going to say, all right, 40 milliliters. So that's going to be 0.04 liters. I'm going to cross multiply. And when I cross multiply here, the number of moles that I have associated with this is 0.05 moles of hydroxide. Now, remember, you can't stop here. It's nice that you found moles. That's good. We're going to actually need that for later. But we're trying to find the limiting reactant. So remember, the next step in finding the limiting reactant is going back and looking at the coefficients associated with Be and OH. And I usually go to the reactant side to do that. So we're going to go up to our balanced equation. We see that for Be, the coefficient associated with that is going to be 1. So I'm going to divide this whole thing by 1. And the coefficient associated with the OH is 2. So I'm going to divide this whole thing by 2. So if I work this out for the top For Be plus 2, I get 0.18. I am not going to put a unit associated with this because, again, the whole process is defining the limiting reactant and the reactant in excess. And then when I do my bottom number, this is going to be 0.025. My next question to myself is, which one is the limiting reactant and which one is the one in excess? The one that's the limiting reactant will be the one with the smaller number. So obviously by comparing these two, I can see that the number associated with the hydroxide is the smaller number. Therefore, this is my limiting reactant. And the larger number will be associated with my reactant in excess. So I'm going to say excess. So where does that lead us? Okay, we figured out what the limiting reactant is. We figured out the reactant that's in excess. But we've just done a calculation here. So the hydroxide ion, the concentration of the hydroxide ion is going to be 0. Molarity is equal to 0. That is what we've discovered here. Whichever ion is the limiting reactant, automatically that molarity will be 0 because it's completely consumed in the formation of this precipitate. There is no hydroxide ions in solution. That is what this is telling us. Now we only have one more thing to do. In this slide, we're going to compare the initial amount of the excess ion before mixing the two reactant solutions to the amount used in the consumption of the limiting reactant ion during the formation of the precipitate. Okay, so what do we know? We know that Be plus 2 is our ion that is in excess. And we know that the hydroxide ion is our limiting reactant. Okay, having that understanding that the hydroxide ion is our limiting reactant, we need to see how much of the Be plus 2 was actually used in order to consume all that hydroxide ion. So in the previous slide, we figured out the moles of each of these. And one of the calculations that you did was you found that the moles of hydroxide in the solution originally was 0.05 moles of hydroxide. Now I need to get out of moles of hydroxide and I need to get into moles of Be plus 2. So I'm going to do a mole to mole conversion here. So I'm going to have moles of hydroxide over and moles of Be plus 2. And when I do this conversion, I am going to look at the coefficients for my equation. So I know that there's a coefficient of 1 in front of the Be, and I know there's a coefficient of 2 in front of the OH. Okay. So when I do this, moles of OH cancel moles of OH. So 0.05 times 1 divided by 2, and this is going to equal 0.025 moles of Be plus 2. Now, that number is the amount used. So we're going to say amount consumed. So in the process of using up all those hydroxide ions, we need 0.025 moles of Be plus 2. Okay, good. So now if we go back and we say, well, what was my initial amount of Be plus 2? The initial amount of Be plus 2, of moles of Be plus 2, was 0.18 moles. Okay, we figured that out by multiplying molarity times volume. So the amount consumed, so we'll say amount consumed, okay, of Be plus 2, which we just calculated, was 0.025 moles. We just did that above. So if we take the difference of those two, our initial amounts, and subtracting the amount consumed as we used up all the hydroxide ions, we find the difference here is 0.155 moles of Be plus 2. So that's the amount of moles of Be plus 2 ions that are still in solution. But we don't want moles, we want molarity. That's what we want here. So now we're going to go back to our molarity formula. Molarity is equal to moles over liters. We have our amount of moles of Be plus 2 that are in excess, so 0.155 moles of Be plus 2, and we're going to divide that by our total volume, so this is going back to 0.12 liters, and if we divide these out, our final concentration of Be ions that are still in solution is 1.29 molarity Be plus 2. So we finally figured out the concentration of Be plus 2 ions in solution. So what did you learn? We went over the pretty complicated process of mixing solutions composed of different soluble solute compounds, resulting in the formation of an insoluble product, otherwise known as a precipitate. We looked at how to get started in the process, which was basically a review. Then we found the concentration of the soluble ions, which was also a little bit of a review. We determined the insoluble ion by finding the limiting reactant. And then we finally ended up going through how to determine the concentration of the ion in excess. And we did all of that by working through an example. Need more help? Feel free to contact me. Have a great day.